Why are you still here? Do we miss something? Laminar and turbulent flow, check. Viscous flow, check. Losses in piping system, check. Still have piping networks involving losses and steady flow energy equation yet. I thought I'm gonna go home early today. Please wait for another video. I need to bring back my bag. Stay tuned. Gonna finish this video right now. Okay, what are we going to do? Reynolds number, we already know about Reynolds number, and then the type of losses, we already know about that. So it's time for the last one, and this one will be about piping network and also about the different applications inside the piping system. So if you're talking about piping network, we have two different kinds of piping network. The first one is called as parallel flow, and the second one is called as the series flow. So this is almost the same as we have inside the electrical parallel and series circuit. Okay, in series, what we'll have is a condition where the piping system is connected to each other. So in series, the volumetric flow rate will stay constant throughout the piping system, even though we have an expansion or a contraction inside the system. Expansion means we are getting a bigger pipe at the end, or contraction means we have a smaller pipe at the end. So it means the volumetric flow rate will always stay constant. This is based from the continuity equation from the conservation of mass. For parallel pipes, what we will have is a condition where you have a piping system branches out into two or more parallel pipes and connected at the downstream of the piping system. So what will happen here is the volumetric flow rate at the beginning will be separated into different parallel piping system. So if you have 2 or 3, you have to add up all these 3 volumetric flow rate to get the volumetric flow rate from the beginning or at the end at the downstream of the pipe. Still, we are still using the continuity equation and the conservation of mass. Okay, that's enough for the piping network. Now we go into 4.5, which is talking about the condition of piping system and how we are going to use the energy equation, which is Bernoulli equations that we learned from chapter 3, and we have to use it but with the inclusion of certain applications regarding to pipe, for example turbine and also pump. However, turbine is something that is rarely used inside a pipe, so we usually depend on the pump to increase the pressure on a certain pipe condition. So, what are the importance of knowing about energy equations, Bernoulli equations, losses, and also using a pump inside a pipe? Okay, imagine having a reservoir at the top of a hill, and then you have a domestic tank at your home. And connecting between the reservoir and the domestic tank is a piping system. So right now, what makes the flow of water moving from the top to the bottom is the gravitational force. So if you have your tank at the bottom of your home and you need to bring the water up to the top part of your home in a bigger tank at the top, for example. So how do you do it? If you want to use gravitational force, it does not go up that way. Usually gravitational force, not usually, it's all the time, it's going downwards. So in order for you to do that, we need to add a pump to increase the pressure at the bottom so that the water will flow to the top part of it. So where is the losses coming in? It comes in throughout the whole piping system. And what happens because of the losses? You will create a change in pressure. So to know more details on this, we have some calculation video after this. So make sure you understand the whole thing, because in this study we will try our best to learn how to calculate all the losses and also to design the right pump for your house. Okay, bye-bye. Hello everyone, welcome back to the final video for this chapter. This is a video about piping networks and also the energy equation in a piping system. So to begin with this video, we will start with piping networks. In a piping system, we will have two different networks, and the first one is called as series and the second one is called as parallel. As I mentioned before, the series and parallel condition is almost similar to what we have with the circuit inside electrical study, which is the electrical circuit. If you are talking about series, it means the connection will go in a straight line from one point to another point. However, if you are talking about parallel, it means we have a condition where we have one inlet and it branches out into two or more branch and connects together at the end of the branch. So this is an example for series and this is the example for parallel flow. Before going further into the study of series and parallel, we have to remember one conservation that we learned through chapter 3, which is called as conservation of mass. Or sometimes it is much easy for us to remember as continuity equation. For continuity equation, we must always remember that if you have flow moving inside an internal pipe, for example like this, doesn't matter whether the diameter is different. For example, this is D1, this is D2, this is D3. We will have constant volumetric flow rate for V1, V2 and also V3. The V dot over here is actually the volumetric flow rate. It means that we can have different diameters. When we have different diameters, meaning we have different area, and when we have different area, it means we have different velocity. So it means velocity at point 1 will not be the same as velocity at point 2 and cannot be the same with velocity at point 3. However, volumetric flow rate for V1, as I told before, V dot 1 is equal to V dot 2 equal to V dot 3. It means V dot 1, V dot 2 and V dot 3 is defined as area of 1 multiplied by velocity at 1, area of 2 multiplied with velocity at point 2, and area of 3 multiplied by velocity at point 3. So the only thing that connects the velocity from point 1, point 2 and point 3 is the volumetric flow rate. So because our study in pipe consists of an internal pipe or internal flow, it means we have to use this definition throughout the study. So conservation of mass needs to be satisfied throughout the system.
Now we will continue with series network. A simple picture for a series network can be shown like this, when you have a piping system connected to each other without no branching out to two or more different pipes in parallel. So it means we have the flow moving from one end to one end. So we will put A on this side, or point 1 on this side, and point 2 on this side, and we have section A on the left side and section B on the right side. Okay, so we also know the diameter at point A will be different than the diameter at point B, and we also have LA may be different than LB, and finally we need to know that the friction factor at point A will also be different than friction factor at B. So at this condition over here in series, FA will not be equal to FB because the friction factor is dependent on the Reynolds number, and the Reynolds number is dependent on rho VD over mu, meaning different diameter will provide different velocity. So different velocity will give you a different number of RE, which is RE at point A will not be the same as RE at point B. So if in case both of them are turbulent, or one of them are laminar and then another one is turbulent, we will have a different number or results for FA and FB. So in this condition over here, series network, the flow rate for each pipe will be the same as we explained in this part. For conservation of mass, the volumetric flow rate will be the same in internal flow condition. So for series network, because a piping system is internal flow, we have the condition of volume flow rate at point or section A will be the same as the volume flow rate at section B. So area A multiplied by velocity in section A is equal to area B multiplied by velocity at section B. However, the losses for the system, HL, will be different because HL from point 1 to point 2 is dependent on the friction factor. So HL1 to point 2 will be equal to HL at section A plus the HL at section B. So for this study, if you have a condition where we have different diameter for A and different diameter for B, we have to do the calculation for F twice, and we have to do the calculation for HL twice, depending on the different section. Why? Because remember, HL is equal to FL over D square over 2G. Okay, we have different diameter, different length, different velocity, and different F. So point A and point B will not have the same major losses. The second network we'll call as parallel. And parallel condition, what happens is you have one inlet and it will be branched out into two or more branches or parallel pipes, and it will be connected downwards over here to this pipe on the right side. So you have one inlet and you have one outlet, and you have two or more branches in between. this condition, as before, we will have different friction for A, or we define this as pipe number 1, pipe number 2, and then this is point A, and this is point B. Okay, so we have different F1, different L1, and different D1. So the same, this is F2, friction factor, L2, and D2. Okay. What do we need to know from parallel condition over here? The pressure at point A will be higher than the pressure at point B. Why? Because we have bends over here, and the flow is moving to a longer length of pipe to the top and also to the bottom section of the pipe. So it means from the length of the pipe and also bends on the side will provide a condition where the pressure at point B will be lower than pressure at point A. Okay, comparing to series, for parallel, the HL or head loss between point 1 and the head loss at point 2 will be the same. This is different than what we have in series. And for volumetric flow rate, V dot here, V dot A is equal to the summation of V dot 1 plus V dot 2, and it should equal to the outlet, which is V dot B. The pressure drop or the head loss between two junctions, junction 1 and 2, must be the same for all paths between the two junctions. This is because pressure is a point function and it cannot have two values at a specified point. So in case we have condition where the piping is going this way and we have a longer pipe on the bottom part, the HL will still be the same for section 1, section 2, which is HL1 will be the same as HL2, no matter how long the length of the pipe in section 2 comparing to the pipe at section 1. So we have covered up the conditions, or we call it as series network and parallel network. So we have covered up the first subchapter of this study, which is the piping network. Now we will continue with the energy equation for a piping system. So let me scroll up these notes. Okay, so now we'll continue with the second part of our video, which is the steady flow energy equation. For steady flow energy equation, we will use the Bernoulli equation as the base for our study. And if you don't remember Bernoulli equation from our last chapter, which is chapter 3, I will revise the Bernoulli equation for you for free. Okay, hopefully you can remember after this. So the base for Bernoulli equation is pressure 1 over, this is specific weight, and this is also equals to rho G plus Z1, which is the elevation height of 1, and then plus V1 square divided by 2 multiplied by the gravitational effect equals to V2 the same rho G plus Z2 plus B2 squared over 2G. Okay, so for Bernoulli equation, it's a study between 2 points, point 1 and point 2. Okay, so for example, if you have a picture like this, point 1, or the first point, sorry, I changed it to A and B, so the equation can be used over here. So PA will be the pressure at the surface of the fluid. So based on the picture, you need to remember, if you are dealing with any assignments or calculation, equations or anything, we need to define the point for our Bernoulli equation. For this question, point A is at the surface of the reservoir at the top, and then point B is at the surface of the reservoir at the bottom. Okay, so point A over here, based on Bernoulli, if it's at the surface and meeting the atmosphere, PA is equal to 0. For PB is having the same condition also, because it is at the surface of the fluid, or usually you have a small triangle here to show that it is a surface. So PB is equal to 0 also. So ZA and ZB will be based on the picture here. This will be your ZA and this will be your ZB. Okay, then Z1 is the velocity. So velocity at this point, point A, is also 0 based on our study in Bernoulli, because the surface does not move that much comparing to the movement of fluid inside the piping system. So VA is equal to 0, and since VB is also at the surface, it is also going to be 0. Okay, if you use the study without ignoring any of the friction inside the pipe, we can just use the basic Bernoulli equation for any of the calculation, meaning this part will be 0, this part will be 0, this part will be 0, and this part will be 0. Oh, so what happened? Z1 is equal to Z2? Is it correct? ZA is equal to ZB? No, it is not correct. It means the Bernoulli equation can be used in this study, but cannot be used without the addition of one other parameter, which is the losses that we learned in our study, which is HL, or HL total. Okay, so from there we can actually find what is the HL total through Z1 minus Z2. Okay, or if we have the HL total, we will find the difference in delta Z or delta Z through HL total. Simple, isn't it? So this is a condition where gravitational effect is playing around with this piping system. Why? If you have a condition like this, you know point A will be higher at the top of the hill, for example, and point B is at the bottom of the hill. So through gravitational effect, the flow will go downwards. Okay. However, if you want to use the same picture and I want to change the direction of flow from B to A, we will have to add H pump, which is the head for pump in our calculation of Bernoulli. So how do we add that? So we'll go to the next page. Ta-da! The same picture again. So this is because of the technology, so I can copy and paste to a different page So right now, what I said just now, we want to change the direction between point B to point A, which is going on a direction that is not following the direction of your gravitational force. Remember, gravitational force is always going to be downwards. So what we'll do is I am going to clean up the flow direction, and we have a picture like this. Okay, so if you have a condition like this, if you want to change the flow from B to A, you cannot overcome the gravitational effect easily. So in order to overcome the gravitational force, we will have to add one application down here. So let me clean up this mess. And the application is called as a pump. Okay, and the ending up of the pump increases the pressure at the point. Okay, so if you apply it at the bottom, it will increase the pressure at the bottom to overcome the gravitational effect and make the water flows from B to A. So, how do we add the pump in our Bernoulli equation? Simple. P1 over gamma plus Z1 plus V1 square over 2G is equal to P2 over gamma plus Z2 plus V2 square over 2G. This is the basic Bernoulli. So if you have an addition of pump over here, it means you are increasing the pressure at point B. So point 2 will be having an additional pump on the right side. H pump, while point 1 Z1 plus V1 square over 2G will be add up with HL total on the left side. Okay, why the HL total change? Because the HL total represents the losses inside the pipe. So for the H pump, it increases the pressure so in the case that we have over here, the direction of flow will be from right to left. So all the losses that we have, it doesn't matter, minor losses, for example the valve, and also the major losses due to the length of the pipe, will be added on at point A, because this will be the amount of losses the pump needs to overcome to make sure that the flow of water flows from point B to point A. So that is why we have to add the losses on the left side, which is at point. Okay. Sorry, keep on forgetting 1 or equals to A over here. And this one too is equal to B. Sorry for the confusion, but you know what I mean, isn't it? So if you have any pump add up to any side, so it must be add up to the place where you increase the pressure, and the losses should be add up at the place where the flow is moving and almost at the end of the system. Okay, so we have pump and we have HL total together. So right now what we want to learn is how do we design our pump based from this equation that we have. So to design the pump, we need to know what is H pump over here. So just now we use the same condition as before. It means point A and point B will have zero pressure, BA and also BB will have zero velocity. So we end up with this equation over here: ZA plus HL total equals to ZB plus H pump. So H pump is equal to ZA minus ZB plus HL total. So if you have the pump head, how do we design the pump? Simple. So the power needed for the pump, or sometimes can be denoted as W dot pump, is equal to the density of the fluid multiplied by the volumetric flow inside the pipe multiplied by the gravitational force, acceleration, and the pump head, H pump, divided by the efficiency. So by using this equation, we just have to put in H pump that we get from this equation over here, the gravitational force, which is always going to be 9.81 meter per second square, the volumetric flow rate, the density of the fluid, and the efficiency of the study. If the efficiency is 1, it means that it is working at 100% efficiency. So if you have 70% efficiency, it means the number that you have to put for this efficiency is going to be 0.7. So this covers up everything that we need to know for the energy equation for a pipe system. So this will be the last video for this chapter, and I think we cover up everything in this chapter. Hopefully you have fun doing all the study together with me in this video and the video before this. Until then, we meet again. Remember, my name is Sham, and I'm from bye-bye.
Okay, so I think we have covered up everything inside our chapter today. So by right now, you should be able to know about the Reynolds number, losses inside the pipe, viscous flow, and then the piping networks, and also lastly knowing about the effects of the losses inside the piping system, and to design your own pump for your own house. Okay, so I'm really sad this is the last video for me. However, I'm able to go back home right now, so I'm quite sleepy. Hopefully we'll meet you again in a different chapter. So till then, remember me, I'm Sham, and I'm from mylearn.my. Bye.